Time is a mystery. It's something we all experience, yet it remains one of the most elusive concepts in the universe. We experience it every day, in every moment, as we go about our lives. We mark its passage with clocks and calendars, trying to make sense of its flow. But what if I told you time is not the same everywhere? What if the very fabric of time could change depending on where you are? What if time itself could be stretched and squeezed, like a rubber band, altering its pace? It sounds strange, but it's true. This isn't just science fiction, it's a reality proven by physics. Gravity, the force that holds us to the Earth, has a peculiar effect on time. It can actually warp time itself. Imagine a vast, cosmic dance floor where gravity sets the rhythm, dictating the tempo of time. Near massive objects like stars and planets, the music slows down. Time itself decelerates. Time itself ticks by at a slower pace, as if the universe is taking a deep breath. This mind-bending phenomenon is called gravitational time dilation. It's a concept that challenges our understanding of reality. Albert Einstein, the renowned physicist, revolutionized our understanding of gravity. His general theory of relativity, presented in 1915, proposed a radical idea. Gravity is not a force acting across space, but rather a curvature of space-time itself. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a dip, distorting the sheet. Similarly, massive objects warp the fabric of space-time. This warping is what we experience as gravity. Think back to the rubber sheet analogy. The closer you are to the bowling ball, the steeper the curve and the slower time moves. Similarly, in the presence of a strong gravitational field, time slows down. This means that time passes slightly slower at sea level on Earth than it does on a mountaintop, where the gravitational pull is slightly weaker. The difference is minuscule but measurable with precise atomic clocks. Section 4. Ticking slower clocks under gravity's spell. One of the most intriguing aspects of gravitational time dilation is that it affects the rate at which clocks tick. This phenomenon, predicted by Einstein's theory of general relativity, suggests that time itself is not a constant, but rather a variable that can be influenced by gravity. The stronger the gravitational field, the slower time moves. This means that clocks in stronger gravitational fields, such as those closer to massive objects like planets or stars, will tick more slowly compared to clocks in weaker gravitational fields. In 1971, physicists J.C. Haffel and Richard Keating conducted a groundbreaking experiment. They aimed to test the predictions of Einstein's theory by taking highly precise cesium beam atomic clocks on a journey around the world. They flew cesium beam atomic clocks around the world, both eastward and westward. These flights were meticulously planned to ensure that the clocks would experience different gravitational forces and velocities. Upon comparing the clocks to a reference clock on Earth, they found that the clocks on the planes ticked slightly slower, as predicted by Einstein's theory. This was a monumental confirmation of the theory of general relativity, showing that time dilation is not just a theoretical concept, but a measurable reality. The eastward flying clock, moving with the Earth's rotation, experienced slightly less time dilation than the westward flying clock, which moved against the Earth's rotation. This subtle difference further validated the intricate relationship between time, velocity, and gravity, providing a deeper understanding of the universe's fundamental workings. Section 5. Proof in the Stars, Experiments, and GPS. The Haffel-Keating experiment provided compelling evidence for gravitational time dilation. In this groundbreaking experiment, scientists flew atomic clocks around the world on commercial airliners. When compared to stationary clocks on the ground, the airborne clocks showed a measurable difference in time, confirming Einstein's theory of relativity. This experiment was a pivotal moment in our understanding of how gravity affects time. But perhaps the most everyday example of this phenomenon is the Global Positioning System, or GPS. We rely on GPS for navigation in our cars, on our phones, and even in various industries like aviation and shipping. Without accounting for gravitational time dilation, GPS would be inaccurate by several kilometers. GPS satellites orbiting Earth rely on incredibly precise atomic clocks to provide accurate location data. These atomic clocks are so accurate that they can measure time to within a billionth of a second. This precision is crucial for the system to function correctly. However, these satellites are situated in a weaker gravitational field than clocks on Earth's surface. This difference in gravitational strength causes the clocks on the satellites to tick slightly faster than those on the ground. As a result, their clocks tick slightly faster. If this discrepancy were not corrected, it would lead to significant errors in the positioning data provided by GPS. To compensate for this discrepancy, GPS satellites must factor in gravitational time dilation, adjusting their clocks by a few nanoseconds per day to maintain accuracy. This adjustment ensures that the GPS system remains reliable and precise, allowing us to navigate our world with confidence.